I have. It's real embarrassing. They've run out of battery power partway through. I'm Tim Salem. I work for Network Computing Services, a company that used to be called Minnesota Supercomputer Center and is recently acquired by a well-funded ASP startup. So my office hasn't moved in the last 10 or 11 years, but I have a whole pile of business cards and a bunch of email addresses. There's some email addresses you can contact me at, and there's also a web page that contains this presentation as well as other information about our project. So let me talk. I'm going to talk a little bit about the research objectives of our project. I'm going to talk about a real-time visualization tool that is focused on displaying the operation of IP protocols in switched environments, particularly IP over ATM environments. We have a tool that's working now. We're looking for a moderate-sized network to deploy it, and we'd be happy to come out and install it and run it on your network if you have a network that looks interesting to us and if you're agreeable. And if we have time at the end, I may talk a little bit more about our research goals, but I think I'll probably run out of time. So, we're working on a DARPA-funded research project that the objective is to explore the behavior of IP protocols in switched environments, particularly in wide area environments, partly because that's where the DoD has the most interest, and partly because when things go wrong, performance torpedoes a lot more quickly in a wide area environment than a local environment. As I think everybody knows, that in a local environment, you just throw resources at stuff and things work. But in a wide area environment with latencies and limited bandwidth, bad things happen more easily. We also believe that techniques for mapping IP streams into a collection of switch connections is a fairly important and fairly general problem. It's important in the sense that there's switched wide area media available. It's often cost effective. We ought to make the IP protocols effective in using that. Also, there's a whole series of protocols that have the same set of problems. IP over ATM protocols is one, but MPLS is a similar set of problems where you've got to maintain this collection of switch connections and assign traffic to those connections. In the course of this project, we've developed a real-time visualization protocol to get a macro-level view of what's happening in some of these sorts of networks, and we're now looking at some place to deploy this tool. So this project started when we were working on the Magic 2 network some years ago, wide area IP ATM research testbed. And we think we detected certain sorts of anomalies, and they appeared to be related to the protocols that map IP streams into SBCs. And it appeared that the protocols were such that if they ran out of SBCs or there was SBC connection in the network, that they would just start to behave poorly. They'd start to thrash. But we didn't have any really good global view of what was happening in these networks. We could get into the Forest Systems console and the command line interface sort of get a view of what one switch was doing, but what we wanted was a global, real-time view that gave a lot of detail and that was a visual view. What we wanted was a picture something like this, and I can actually run. This is based on a very primitive version of the tool and very old data from the Magic testbed, which doesn't exist anymore. There. But then what we wanted was a snapshot like this. Now this is actually just a sequence of GIST files, but it was a snapshot of data that we took a long time ago, every 10 minutes or so of the Magic testbed, and you can see the activity in a primitive sort of fashion, activity in the network. You can see where the switches are in the X boxes and the hosts that are empty boxes, and these yellow lines happen to be the UNI SBCs. Now there's a bunch of other stuff that we deleted from this diagram, but this is what we wanted in a crude form. We wanted to get this global view of what was happening with switch connections in this network, and we wanted it in real time, whatever real time means. We really wanted it as quickly as we could generate it, and we wanted to generate it in a passive sort of way. We didn't want to have to go out and instrument the network. A couple of other features I'll talk about it because it's not in my later demo. We also have this ability to group nodes into areas and label those areas with the geographic area, and generally provide the researcher with some control over how these nodes are displayed on the screen. So let me close this just because my machine is just horribly short of memory, and I can get this thing to page at 2,000 some pages a second if I'm not careful. So anyway, that was our objective starting out, and that was an early view of the tool. Now, as we continue to develop that tool, talk about the current state of the tool. So what it currently does today is it displays graphically in real time, meaning as fast as we can collect the data, IP-related streams in wide area, IP-ATM internets. By IP-related streams, I mean that we try to color encode attributes of those virtual circuits in a variety of fashions. We can determine whether these virtual circuits are primarily used, for example, to an ATM ARP server, or to a WAN server, or other protocol-related issues, or we can encode them in other fashions that I'll show in a moment. But like I say, the tool, while it could be extended fairly easily, its focus is this set of protocols that maps and maintains this collection of switch virtual circuits. And as I hinted at already, this tool allows the researchers to interactively control the visualization process. Obviously, if you look at everything simultaneously, you can often get just a jumble of who knows what. And so it is desirable to have some ability to control what you're viewing. And we provide that. Also, we can store and replay data, and in fact, we can create these animations as I talked about in a moment. And initially, we support IP-ATM, but there's nothing that, as they say, just software. So there's nothing really much preventing us from extending it to a variety of other environments. So the tool is written in Java. We started with a blank slate so we could decide to do anything we wanted, and we decided we wanted to do a project in Java. It was an interesting exercise. I don't think we did the wrong thing. Not sure I'd want to write production protocol software in Java at this point in time. That we fought with a lot of performance issues. But nonetheless, it was a great exercise, particularly as an exposure to an object-oriented development environment. The stuff compiles under Java 1.1 in part because the visualization application can run as or typically will run as an applet, and most browsers won't support Java 1.2. But a whole bunch of stuff works better if we compile it under Java 1.2. Unfortunately, the version that I have on my laptop is Java 1.1 because I just sucked that down off our web pages without recompiling it. And we will release the software with a Berkeley-style copyright when we're done with the project. It's probably not ready for release yet. If anybody's really hot to have it, we're happy to provide it now, but probably we are waiting until we were really done. It's sort of that a beta comes with a programmer stage at this point. We did a whole object-oriented design. We use UML and everything to define a class hierarchy to describe how we're going to model these networks. And you can even run Javadoc over this source code and get pretty good documentation on the classes. So visualization tool is composed of really two major parts. There's this data collection and analysis subsystem at the lower part of the picture, which sits on or close to the network and selects data out of the network using SNMP, and creates and maintains a model of the network, and then ships updates off to the visualization subsystem, which then creates the visualization. And I just said that. So the collection analysis subsystem extracts data from the network using the SNMP. Our objective was to be able to, if you will, walk into a network with just a box and plug it in and not have to worry about instrumenting the network or tapping octave-row lines and sucking up packets. And besides, you can get a view of one part of the network that way, but the only way you can really get a global view of the network is go and pull everything in the network and ask those devices what they think their states are, and then compile all that. The software auto-discovers the topology of the network. You give it the address of a node, and you give it a list of SNMP community names, and it goes off and searches as far as wide as it can until it runs out of community names. So that's about the only configuration you need to do in order to get this to come up and start providing a picture of your network. This data collection analysis subsystem creates a model of the network. There's, if you will, a model of both the topology and the state of the network. There's, if you will, there's a network class which contains a number of switch classes, and there's a number of link classes that interconnect switches, and there's a number of virtual circuit classes that go from host to host typically, and then there's these other things, that these sort of partial virtual circuits that we haven't yet found all the pieces to yet that appear from time to time. So we have, if you will, create a graph of the network, and we associate attributes with those classes. A link attribute is going to have some sort of number of bytes per second, or number of cells rather, that have been transferred across it, and length of time it's been up, and so forth. And we can at this point easily associate new attributes with these classes. If it's in the MIB, we can select it out of the MIB, stick it in the class in the model, and ship it off to the visualization program. And as the topology and state of the network changes, the data collection analysis subsystem sends model updates to the visualization subsystem. And these model updates are serialized Java objects, which means, well, a couple of things. One is you can just write them to a file and use them to a file again, since they're just byte streams, serialized Java objects. You can do anything you want with them, I guess. And also that we can create the complete model as a series of updates. As a browser comes up and talks to the data collection subsystem, the browser is told, well, I discovered a network, and I discovered a switch, I discovered another switch, I discovered a link between the two switches, until the model in the visualization subsystem is consistent with the model in the data collection subsystem. Visualization subsystem runs either as an applet or an application. Typically it's going to run as an applet because that's what makes sense. You just embed it in the browser page or web page somewhere. Or it can run as an application, which I'm going to try to do here. But like I say, I've gotten my PowerPoint or my laptop to page at 2,500 pages a second, and things kind of grind to a halt then. And this visualization tool receives updates either from the data collection subsystem, or you can just read them off the file, which is what I'm going to do in a moment. And it maintains a parallel model of the topology state of the network, parallel to what's maintained by the data collection subsystem. They're different classes. Let's say they're both subclasses of the same class. The visualization subsystem needs to remember where a switch is located on the screen, but doesn't need to remember a community name, and the data collection subsystem has the converse requirements. But they're subclassed, and so, given a object-oriented language, you can play lots of neat games with those sorts of things. And the operator has some ability to control the visualization process. So we have this running on small networks. If you look at our web page, it's displaying it's displaying our internal network, which has one switch and a half a dozen hosts, which is really dull. And it's displaying what we call a university network. It's displaying a somewhat larger ATM network at the University of Kansas. And as long as we can keep that connection up to Kansas, that's available live on our web page. As we did this, we found that there's less information in the MIBs than we had hoped. We found, of course, that standard MIBs aren't always implemented, that vendors will start out putting stuff in enterprise MIBs, and eventually they may move to a standard MIB, but, switch developers are like everybody else. MIBs aren't first on your list of things that we're going to go off and implement. Again, it's no surprise either if you watch the process that MIBs appear to be designed to expose implementation variables, not to provide the sorts of information that we want out of the MIB or out of the device so that we can generate these nice visualization pictures. But we're ready, and we're eager to deploy this on some larger networks. That's one of the reasons I'm here. But I'd be more than happy to talk to anyone who's interested in running this, and I'll talk to them about it in a moment. So let me do a demo here. I'll also note, speaking of learning how to use PowerPoint, really bad things can happen if you try to use URLs within PowerPoint. No.
So you want using that?
No, I'm just going to run this from my laptop. I'm all set. It's not that I don't trust this networking stuff or anything, but and it actually run a little bit better over laptop. So, but this is the current tool running as an application, just running off JDK 1.1 in my laptop. And so this is data that we collected this is a model composed from data that we collected from University of Kansas last week. And as you can see that there's all the switches, they're identified as the X's. You can click on a switch and get information about that switch to the extent that you can extract it. And again, if there's other information anybody wants, we can do it now that we have the process of getting the information out of the switch and into the display application. But again, this is all pre-recorded data, and now we'll have to wait for my laptop to thrash here for a few minutes. But I was hoping by shutting down PowerPoint. I could get my memory bank, but didn't. And so we color encode the virtual circuits. In this particular example, we currently have it set up to color encode by signaling type. And so you can see that the yellow ones there are U and I. These happen to be 4 system switches, and for historical reasons, there's still spans running there. The green lines, you know, it runs forever. You don't need to configure it. It's a neat solution. And then the blue lines happen to be signaling channels. Let me close these things. Oh, so here we have information about a port where we actually create a graph over time of the utilization of that port. You can click on a VC and gain information about that VC. We happen to know how long this VC was up and what sort of traffic has been passing. And you can drag these things around and so forth. Also, you can control, like I said, go off and run this on your web browser, because it really will run better on your web browser than it runs on my laptop, but I didn't have time to debug Windows. You can control, you can turn on or off, for example. You can get rid of all the U and I VCs and see what's left in terms of spans, and signaling happen to be the primary things. We also can color encode VCs by age, and about the only interesting thing you find there is that, I guess not too surprising, that VCs are sort of bimodal. Either they've been up all day long, or in this case for days, or they've been up for just a few minutes. And you know, that's an artifact of what part of the IP stack is driving those VCs and some of the traffic patterns and some other things, like Arizona that was up for a long time. We can also encode by data rate, but currently this is encoded as the percentage of the bandwidth that's totally utilized, and as you can see, basically this thing's underutilized, so everything looks red. But nonetheless, we have the technology that allow you to do that, as well as some other things there. So that's a quick overview of the tool. Oh, and as I said, you can drop and drag these nodes around and save the configuration information and reload it, and then have all the future animations use that same configuration. Let me fire up PowerPoint again. So, at this point, we've got a set of technologies. We're looking for a moderate-sized network on which to deploy this tool. Ideally, a wide area network, since that's really where the motivation for our research project came from. This thing is oriented toward IP over ATM networks, meaning classic IP or WAN. You know, to the extent that we have funding, we'd be happy to take a crack at MPLS. We have not looked at an MPLS switch, and I am a bit concerned that, given the maturity of the MPLS products, that the MIBs just may not be there adequately to really extract enough information to get a nice picture of an MPLS network. But obviously, over time, if you'd like the same sort of high-level, fine-grained, real-time view of what's happening to your connections, if you will, in an MPLS network. And there again, if anyone's interested, we'll come out and install and run the tool. We'll put a person on site if necessary, and we will add support for your switch vendors' MIBs, because stuff's probably in the enterprise MIBs, and so we probably haven't done it yet. And to the extent that we have time, meaning that until we run out of time and money, probably the end of the year, we intend to keep extending the software, and if people have things that they really like to see out of their network and it looks interesting from a research standpoint, we're happy to do that. And in addition to that, we probably would like to sort of work on the next layer outside of our network and be able to extract information about LAN switches, Ethernet switches that are connected to the ATM network or the routers. And if you want more information on the visualization project, there's a URL that will get you to the visualization project. And there's my email address. Now, I think I got done a little quicker than I projected. I've got still a few minutes. I'll make just a one or two comments about our research project. Oh, there's terminology that I use throughout here that I think you may notice. MPLS had a nice term for stream, which is just an aggregation of flows that you switch at either layer 2 as a collection rather than as individual IP flows. Now, I'm not sure I ever understood exactly what flows were, and I'm not convinced that any two people had exactly the same definition. So it's nice at least that MPLS folks provided us a little bit better definition. As I said, we think managing a collection of switch circuits and forwarding traffic over them is a really general problem. IP over ATM has a collection of techniques for doing this sort of thing that are all a little bit different, only the same, only different. We have MPLS, which has a similar sorts of, performs a similar sorts of functions, as I'll show in a moment. One could argue that mobile IP tunnels are another class of a switched connection over which IP protocols have to forward traffic, and it would be interesting, I think, to see in a global view all the mobile IP tunnels that are existing in a particular network at one time and see how they come and watch as they come and go. Now, we haven't gone to look at the MIBs to see if we can in fact extract enough information out of those devices to create that. That certainly is a picture that I think would be interesting for someone who's running mobile IP. In a similar fashion, and we've not even come close to attacking that, but approaching this, but you know, you'd like to see what your ISVP connections look like. And I think, you know, I don't think there's too much debate here that at least parts of the IP protocols don't work all that well over switch connections. Routing protocols don't necessarily respond gracefully to rapid and particularly large topology changes, and in fact there's a lot of techniques to, if you will, really avoid this, and for example the IP over ATM protocols. Now, just as an analogy as to why this might be hard, you know, the process of installing a leased line takes a long time and has a whole lot of manual processes. I just arbitrarily picked 100 days. Between the time that you decided, geez, I need a little line between this router and this router, this is what its bandwidth ought to be, and get it installed, and then it doesn't work, and get it to work, and then get your router configurations fixed. I mean, that takes a long time. There's a whole bunch of manual intervention. And what switch connections are, in the worst case, is they're trying to do all that 100 days worth of work in 100 milliseconds. And so it's understandable that maybe we haven't got right like that. And we think we can break, and where can things go wrong? And the things that we've seen are just difficulty in maintaining the collection of these connections in terms of stability was where we first saw this. And this is why we wanted those real-time pictures to see how stable that connection of connections, stable that collection of connections was. And once you have the picture, of course, then you start asking questions, geez, why is there a connection between here and here and not here? Or what happens is you see, particularly depending on how your switch is figured, if you run out of VCs. There again, we think that this global picture is at least something to help researchers and I think operators understand the behavior of some of these protocols. So with that, I think I have about 5 minutes left, and I think I'll break and take questions at this time. Oh, just one final comment. That it's also our assertion that a lot of these programs, particularly in wide area networks, you can configure networks poorly and have problems. But it's our assertion that we haven't yet don't have a good collection of design rules for designing protocols that work in particularly the anomalous cases well in wide area networks. And that's part of what we wanted to drive at, is at least to point out at least point to some protocol design techniques that either are bad or could be improved upon. So with that, let me take any questions if there's questions in the audience.
Just what's your schedule for when you intend to release the full product, or the full app? Or are you going to release it early in sort of beta format?
My answers are send me email, and you're happy to look at this stuff because we've already made a commitment to release it with the Berkeley style license. We're happy to make it available to anybody. If you want to run it, we're happy to come help you run it. Ultimately, we're going to run out of money and contracts in December, by which time we've got to have it bundled up and released. So the stuff works. You know, look at our web pages. The stuff works. As we get to a larger network, we'll probably find some things we want to do differently. Probably a little bit of performance optimization. But if you want copies of the stuff, send us email.
And then how about concurrent visualization of the real-time statistics? multiple users accessing?
Yeah, the collection and analysis subsystem can support multiple users, and that's why we have that mechanism there where the first thing that happens when a browser comes up is it dumps the current model to the browser. So you can have multiple browsers now. I won't claim we've had more than 2 or 3 running simultaneously, but yep, that's the intent, and it seems to work.
Thanks very much, Dick.